Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Thambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for the BSc Physical Sciences students for the paper on applied electronics. We are going through a set of lectures under the chapter on quantum mechanics, which starts with uncertainty principle, postulates of wave mechanics, in general the various aspects related to quantum mechanics. And contents of lecture 1 are given here: differences between classical mechanics and quantum mechanics, uncertainty principle, observation of the electron, inherent problem. Now, first of all, as students of science, especially doing applied electronics, what is electronics? Electronics is nothing but electron dynamics, the movement of electrons, without which you cannot explain the passage of current in your semiconductor circuits, the working of cell phone and so on. They all depend upon the electronics or movement of electrons. What are electrons? Whether electrons are classical objects like the one that I have here, you know, the celestial bodies are classical objects for which the classical laws or they come under classical mechanics. So, let me now first discuss about the differences between classical mechanics and quantum mechanics. Who is the father of classical mechanics? What is classical mechanics? People like Isaac Newton, who laid down the laws of motion. Laws of motion for what? For macroscopic bodies like the celestial bodies, the movement of planets and so on, they are the macroscopic objects. What about this object that I have in hand? Is a classical object. A cricket ball is a classical object, right? Okay, you can have billiard balls, cricket balls, and automobiles. They are all macroscopic bodies which have to be the classical laws of motion or Newtonian dynamics. In a classical dynamics, classical mechanics. On the other hand, you have got microscopic particles like electrons, protons, and neutrons, which will not be the mechanics which was given by Newton, Galileo, Kepler. You have heard of Kepler's laws of planetary motion, and those laws will go wrong, cannot be applied to the case of electrons, protons, neutrons, and so on, and hence you pass on to what is called quantum mechanics. So, the classical systems, as I told you, cricket ball or automobile, etc., can have continuous energy values. I have a ball here, I can hit the ball with an object here, I hit the ball here, you know, the ball moves, right? the ball can be made to move with any velocity. Now the ball is moving with any velocity or any momentum is allowed, and not only that, the position and the velocity, both of them can be simultaneously measured. You should remember the position and velocity or the momentum. Both the position and momentum can be simultaneously measured for a classical system. You talk of a cricket ball, the ball can be hit in such a way you get 1 run or 2 runs or 4 runs, you get a sixer, and therefore the path taken by the cricket ball can be in any direction, and the velocity as well as the position can be simultaneously measured. If you take an automobile or if you take a electric train, the train is passing through a station, and at a given instant of time, what is the velocity with which the train is moving? Suppose it doesn't stop at a station, it is traveling at a particular speed, 60 miles per hour. You know, the speed is 60 miles, the speed multiplied by mass, the velocity multiplied by mass gives the momentum. So the momentum of the carriage or the momentum of the train as well as the position, it crosses a particular station. So at a given point of time, at a given place, and at the velocity and momentum or the momentum and the position can be simultaneously measured for classical objects. And not only that, the ball can be raised to any height. So the what is potential energy? The mgh, right? So I can have here or here or here. So the continuous energy values will be possessed by classical objects. For instance, as far as I am concerned, if I run in the ground, I can run with any velocity. I can walk or run with any velocity. Therefore, the momentum of the body can have continuous values, and so the energy is continuous. Okay, the energy of the ball is continuous, whether it is kinetic energy or the potential energy or the total energy will be continuous. Now, what about the microscopic particles? I told you the microscopic particles are electrons and so on. They will not have continuous energies. That is what we are going to learn at the end of this chapter. When we pass on through the whole of quantum mechanics, you will understand that the electrons or protons or neutrons will have only discrete energies. And not only that, if you take classical objects, see, these are classical objects, you can see that they are macroscopic objects. You know, the coins in the carom board, right? I can have any number of coins, right? This is the energy level, right? With respect to this room, one energy level, and this is another energy level, this is another energy level. Okay. Now, in a given energy level, in this energy level, how many carom coins I have got? 1, 2, 3, 4, 5. I have got 5 coins, or I can put any number of coins. I can have 100 coins to occupy a particular energy level. This energy level, the energy corresponding to the top surface of the table, in this top surface I can spread 100 carom coins. All the 100 carom coins will have the same potential energy. Now, what about the electrons or what about the protons? Whether this particular thing is obeyed. There is no restriction in the number of classical systems, they are classical objects, to occupy a particular energy levels. On the other hand, in quantum mechanics, we will have discrete energy levels, and again with regard to occupancy, you will have only a certain number of electrons. You have the Pauli principle, which says that in a given energy level in the hydrogen atom, point number 1 is for quantum mechanical objects, the energies are discrete, they are energy levels, right? The first energy level, the second energy level, the third energy level, fourth energy level. So the energy levels which the electron can occupy in the hydrogen atom, or the electrons can occupy in a molecule, any molecule, methane or hydrogen or chlorine molecule or atom or molecule. Now, the energy levels are discrete as far as electrons are concerned, or protons are concerned, or neutrons are concerned. They will take only definite energy values. Okay, unlike the case of a ball, here I can raise the energy continuously for a classical object. On the other hand, for microscopic systems like electrons, protons, the energy levels are discrete. The second thing is you ask the question in the first state, this is a K shell. I told you in the Pauli principle, the number of electrons that can go into the K shell or the first quantum state is only, you write 1s2. Only 2 electrons can be found. Then you write 2s2, then 2p6. Therefore, you can have only certain number of electrons in a given energy state. On the other hand, with regard to Karam coins, I have any number of Karam coins on a corresponding to a particular energy level. That is allowed in the case of classical mechanics, but in the case of quantum mechanics, one should remember that the Pauli principle holds good wherever you got electrons. Electrons in atoms, electrons in molecules, or electrons in solids. Very often we find that the students are unaware of certain things like whether the Pauli principle can be applied to electrons in solids. The Pauli principle is very general. It should be applied to the electrons in atoms, electrons in molecules, electrons in solids also. When you go to the electrons in solids, this is a case that you got the particle in a box problem that I will do after 4 or 5 lectures, wherein you find the lowest energy level is occupied by 2 electrons, one with spin up and another spin down. So you should understand every energy level will be occupied only by 2 electrons. This is the Pauli principle. Pauli principle states that you can have in a particular energy level, you can have only 2 electrons, one with spin up, the other with spin down. So you got spin up electron here, the spin degenerate. The 2 electrons having the same energy state is called degeneracy. Degeneracy means 2 eigenstates or quantum states having the same energy level. So the energy level which can hold 2 electrons, then the other 2 electrons should go to the second state. In the case of atom, take the case of lithium. What atomic number is lithium? The atomic number of lithium is 3. Can you put all the 3 electrons in the same shell, the first shell? It's not possible. You write 1s2 and 2s1. So necessarily the third electron should go to the second shell. The first shell will hold 2 electrons and the third electron has to go to the second shell. It is because of the fact that the Pauli principle should not be violated, or in other words, electrons should obey the Pauli exclusion principle. The Pauli principle excludes the possibility of having more than 2 electrons in a particular energy state. So you got 2 electrons here, 2 here, 2 here, and so on. The topmost level that you know is called the Fermi energy. We'll come to that later, but anyway, the point is, unlike the classical physics wherein I can have any number of Karam coins in a particular energy state, here you got only 2 electrons in a particular energy level. Okay, so these are the differences between the classical physics and quantum physics. As far as this lecture is concerned, I should like to bring back to your memory the fact that I told you that when you have a train passing through a particular station, the momentum of the train as well as the position, both of them can be simultaneously measured as far as the train is concerned, or as far as the cricket ball is concerned. What is the velocity with which it's traveling when it is crossing the boundary? You have got the boundary, your person is able to hit the ball and it is crossing the boundary line, the position is the boundary line, and what is the velocity with which it is traveling, crossing the boundary line. Both of them can be simultaneously measured for a cricket ball. Okay, so the quantum mechanical systems, how many electrons you can have in a particular energy state that I showed you just now. So the Pauli principle lays restrictions. In classical mechanics, the energy and momentum can be measured simultaneously. Is there any problem with regard to the above in quantum system? In a quantum mechanical system, the important point is the position and momentum cannot be simultaneously measured accurately. I will have a break at this point. Welcome back at the break. As I have been telling you, when you think of electron, its position and momentum, both of them cannot be accurately measured simultaneously. At a given instant of time, the position and momentum cannot be measured accurately. This is found out by Werner Heisenberg, who lived from 1901 to 1976. Here there is a famous statement, you are probably here. That means you talk of probability. From now going to talk about uncertainty. You know the difference between probability and certainty. Certainty is I am asking the question, are you coming tomorrow to the class? If you say yes, that is certainty. Uncertainty is the one that comes when you go through quantum mechanics. By uncertainty you mean the impossibility of measuring the momentum of the electron and the position of the electron, both of them accurately. It is impossible, or there will be inaccuracy, right? If position is measured accurately, the momentum cannot be measured accurately, and vice versa. Heisenberg was a German theoretical physicist and one of the key pioneers of quantum mechanics. He published his work in 1925, the breakthrough paper on the perpetual concept of quantum theoretical kinematics and mechanics. He got the Nobel Prize in 1932 for the creation of quantum mechanics or matrix mechanics. So this is the Heisenberg's famous uncertainty principle. The way Heisenberg originally stated the principle is as follows: if you can make the measurement of any object, you can determine the x component of the momentum with an uncertainty delta p. Delta p is the uncertainty related to the measurement of momentum. You cannot at the same time know its position more accurately than delta x. Delta x is greater than or equal to h bar by delta p, or in other words you can write delta x into delta p is greater than or equal to h bar, where h bar is a definite fixed number given by nature. This is how he stated. You know what is h bar? H bar is nothing but h by 2 pi. H bar is a unit of angular momentum. All of you should be knowing by now h bar is the unit of angular momentum. It is called the reduced Planck constant and is approximately 1.05 into 10 to the power minus 34 joule second. The most important point is, what is Heisenberg uncertainty principle? It is the mathematical statement is delta x into delta p is of the order of h bar. Okay, what is delta x and delta p? Delta x is the uncertainty in the measurement of position, and delta p the uncertainty or the inaccuracy or indeterminacy in the measurement of momentum. X is position and p is the momentum. So the position and the momentum of an electron or a proton or a neutron or pion or meson, when you go to microscopic particles, they cannot be measured accurately simultaneously. This is very important. Simultaneously, both of them, position and momentum, cannot be accurately determined. So the inaccuracy in the position measurement is delta x. delta P is the inaccuracy in the momentum measurement. I will now pass on to one of the famous stamps issued in recognition of the important work done by Heisenberg. It is delta P into delta Q is H cross is a famous Heisenberg equation. The uncertainty principle is stated like this: Q is the position and P is the momentum. Now supposing I will again state in this form: delta x into delta P is H cross by 2, or the energy time uncertainty delta E in delta T is equal to H cross by 2. Okay, the conjugate variables x and p are called the conjugate variables. So delta x into delta P is equal to H cross by 2, or H cross by 2, or H cross by 2 pi. Various things have been, results are obtained. Supposing I want to measure the position of the electron accurately, what will be the inaccuracy in the momentum? You look at the equation here: delta x into delta P is H cross. Okay, what is delta x? Delta x is the uncertainty or the inaccuracy in the measurement of position. Okay, if I want to accurately determine the position of the electron, that means delta x will be equal to 0. I should make delta x is equal to 0, right? If delta x is 0, what is delta P? Delta P will be H cross by 2 multiplied by delta x, right? Delta P is what? Delta x will go to the right hand side, where? To the denominator. If I want to fix the position of the electron accurately, then delta x should be equal to 0. The inaccuracy in the position measurement should be equal to 0. If in the denominator delta x is 0, means what? What will happen? H cross by 2 into 0, 0 comes in the denominator. So what happens to the right hand side? Right hand side becomes infinity. Delta P will go to infinity. That means what? The inaccuracy in the momentum measurement will be infinity. You know, the momentum cannot be measured accurately at all, or the inaccuracy becomes infinity if delta x is 0. That means if you try to measure the position accurately, the inaccuracy in the momentum will become infinity. Okay, and vice versa. If you want to measure the momentum accurately, the position cannot be measured accurately. If you want to measure the momentum very accurately, that means delta P should be equal to 0, delta x will go to infinity. Okay, so the inaccuracy in the position measurement will go to infinity. Okay, this is a very important principle. Delta x, delta P, delta E, delta T are the uncertainties in position, momentum, energy and time respectively. Okay, the uncertainty principle is also known as the indeterminacy principle. You go from deterministic physics, the Newtonian dynamics, or the classical physics, or the classical mechanics, where things are deterministic. The position and momentum of a moving ball or moving train simultaneously can be measured. They are the macroscopic bodies. When you go to microscopic objects like electrons and so on, both of them cannot be measured simultaneously in a very accurate manner. That is the Heisenberg's uncertainty principle. What is the inherent problem? You want to see an electron, right? You want to observe the electron in a microscopic body. This is a ball that you can see, right? This you can, all of you can see. Now I ask the youngsters, you are here, how will you see the electron? You see the object here in the visible region, right? The object is so big, you see the object. Now I ask the question, what is the size of the electron and how will you see the electron? You should be knowing the so called Rayleigh's criterion. For any object to be seen, you have to shine light. If the whole room is made dark, will you be able to see me, or will you be able to see the gentleman who is sitting opposite to me? I cannot see him and he cannot see me, and everything will be dark. So you need light. What kind of light you should use to see me? You are using white light. Now if you want to see the electron, what kind of radiation should be used? So the question is, what is the radius of the electron? The radius of the electron is the order of, you don't worry about the numbers. The important point is the radius of the electron is extremely small, 10 to the power minus 15 of a meter. The Rayleigh's criterion says that I want to see any object, then the light that I should use to see the object should be of the same magnitude as that of the object. The diameter or the radius of the electron is in the order of 10 to the power minus 15 of a meter. Then if you want to see the electron, then I should use the light whose wavelength is of the same order. That is very important, right? If you want to see me, then you should make use of white light. Similarly, the Rayleigh's criterion says that any object were to be seen, then the size of the object and the size of the wavelength of the radiation that is used, both of them should be of the same order of magnitude. Therefore, if you want to see the electron whose size is 10 to the power minus 15 of a meter, then look at the electromagnetic spectrum. You have got the entire electromagnetic spectrum. In the whole universe, you have got radiation in very many kinds of radiation: ultraviolet, infrared, gamma radiation, X-rays, and radio waves, and so on. Where does it lie? You are interested in 10 to the minus 15 of a meter. You see here visible region here. It is an angstrom, right? You see here gamma radiation. You see the atom X-ray here, right? X-rays are used to see the atoms in solids and so on. Now you have got 10 to the minus 15 of a meter of the size of the electron, and so you have to go somewhere here. I have the arrow here. That is, your 10 to the minus 15 will be here. High energy gamma radiation should be used. The point I want you to understand is, if you want to see the electron, you have to use high energy gamma radiation whose wavelength will be of this magnitude, 10 to the minus 15 of a meter. That is dictated by Rayleigh's criterion. The criterion which says that how the objects can be resolved. So you have to use this kind of radiation. This radiation that you are going to use, high energy radiation, that high energy radiation, when it interacts with the electron, it will throw the electron out of the field of view. If you want to see the electron at the origin, at the crossfire, at a point x equals 0, y is 0, but the result that you get is the electron will be completely thrown out. So the inherent problem which I am talking about, I will have to deal with it in the time to come. And as far as this lecture is concerned, I should now summarize the lecture. In classical mechanics, energy and momentum are continuous. In quantum mechanics, they are discrete. In the former, both can be measured simultaneously, whereas in the latter, there is an inherent difficulty in measuring them at the same time. The uncertainty principle states that the product of the uncertainties of the position and momentum is the order of Planck's constant. The questions for this lecture are: state the differences between classical mechanics and quantum mechanics. What is the radius of the electron? How will you see the electron? What is the inherent problem in seeing the electron? State the uncertainty principle. And in the lectures to come, I will go through the details with regard to the inherent problem in seeing the electron and certain other associated things with regard to uncertainty principle, and then build up the basics of quantum mechanics and their applications. With this, we come to the end of the lecture number 1. Thank you.